let me get started. Thank you for your homeworks, I think. 3, 4, wait a minute. 1, 2, 3, 4. But there are, all right. All right, I will pray. Heavenly Father, we thank you for this day. I thank you for these students. And I just pray that you be glorified in what we do and help us all understand a little bit more about topology in the plane, Lord. In your name I pray, Lord Jesus. Amen. Okay, so today I'm talking about topology and limits. And not in the abstract, of course. I'm talking about topology and limits for the complex numbers. All right, so first of all, the most basic thing to introduce here is the notion of a disk, an open disk. So we let epsilon be greater than 0 and z naught be in the complexes, all right? Then the disk of radius epsilon centered at z naught is what it sounds like. It's a disk of radius epsilon centered at z naught. Now it doesn't include the edge of the disk, so you might call it a fuzzy disk. So it's z and c such that the distance from z to z naught is less than epsilon. All right. This is the open disk of radius epsilon centered at z naught. So a picture of it is something like this. Here's my z naught, and typical point in here is z, right? And it's that whole collection of points. That's the open disk of radius epsilon centered to z naught. Now, let u be a subset of c. All right. Then if z naught is an element of u, we say z naught is an interior point. All right. If there exists an epsilon greater than 0, for which the disk of radius epsilon centered at z naught is contained in u. All right. And if each point in u is an interior point, then we say u is an open set. All right? So this is what an open set is. Another definition I should make for you, if u is a subset of the complex plane, then the boundary of u, which we don't denote like this, is equal to the boundary of u is the set of all points for which there exists an open disk which contains points in u and points in the complement of u. All right. So this is z in the complexes such that how did I say it? There exists epsilon greater than 0 such that the disk of radius epsilon centered at z contains points both inside and outside U. I wrote that in a sentence. Let me write it in terms of like set theory. Let's see here. So I could say that like the disk of radius epsilon centered at Z intersected with U is non-empty, and the disk of radius epsilon centered at Z intersect with the complement of U is non-empty. So C, you guys know what C minus U is? This notation in here, C minus U is equal to the set Z in the complexes such that Z is not an element of U, right? This is the complement of U in the complex numbers. So then, definition, if the boundary of U is a subset of U, then we say U is a closed set. There's a theorem you could prove, and you probably would prove this in like a topology course, which is not too hard to prove, but this is the theorem, which is that U is closed if and only if the complement of U is open. That is usually taken as the definition of a closed set in a course in topology. That tends to be what I just wrote in blue, taken as the definition. It's equivalent to what I wrote about the boundary, but anyway. So far, so good? Got a lot of language to settle here. So some elementary theorems you can prove. If U and V are open, then U union V and U intersect V are open. And the same is true if they're closed. Like the union of two closed sets is closed, the intersection of two closed sets is closed. I'm not really going to get much further into that business here. That's kind of more the province of topology proper, but you can prove that an arbitrary union of open sets is open, but it's only the case that a finite intersection of closed sets is closed. You can't expect that an arbitrary intersection, an infinite intersection of closed sets is closed. It doesn't work that way. So there's a difference between open and closed in that regard. Let's see here. So let me just give you guys a quick example here, sort of geometric, and I'll attempt to. So let me draw a picture like this. So suppose this is the set. So I'm including dotted lines for the points that are not in, solid lines for the points that are, like that. All right, and then we're going to assume that the interior, like the inside of that, which you know what it means because, well, there's a meaning to interior, right? That's kind of intuitive. So all those points are in there as well. So that's my U. All right. And let's see. Let me make it a little bit more concrete. So U could be like it could be like Z in the complex plane such that 1 less than or equal to the real part of Z less than or equal to 3, and I don't know, -2 less than rather the imaginary part of Z less than, I don't know, 10. well, I guess that's not the scale. Maybe if that's 2, I guess it's 0. There. All right, fine, whatever. So if I do that, then you can tell me like what the corners are, right? Like this point up here would be what?
3, 0.
3, yeah, just 3, right? And this point over here? It would just be 1, right? Now, I guess this one's a little more interesting, right? That would be 3, what? 3 minus 2i? And this guy over here would be 1 minus 2i, right? That's not topology, that's just visualizing complex plane inequalities. Okay, guys, so my questions for you are, let me just use the red marker, pick a point, like right here. Is this an interior point? Why? Let me ask it a different way. Why is this an interior point? If we're just going to operate graphically, right? You could draw a picture, right? You could draw a little like that, right? There's some radius epsilon disk centered at that point, which is inside the set U. Therefore, that's an interior point. Okay? Does that make sense? I hope it makes sense. On the other hand, if we were to look at, say, this point right here, which perhaps would be like 3, I don't know, minus I over 2, perhaps. This is not an interior point, right? Why? Look at it. No matter what epsilon disk you put around that, do you get a subset of U? Look at it. It doesn't matter. How small you make the epsilon, you've always got points here outside U, right? So only this part is inside U. Ah, what does this make? Yeah, what does it make it?
Wait, I had a question.
Okay.
So if that point was just inside of that line,
Yeah.
then it would be classified as an interior.
That's right. Because you could make epsilon sufficiently small to wrap around it, yeah.
So that's a member of del U, the boundary.
Yeah, that's in the boundary, right? So, in fact, because no matter which, because there exists epsilon such that we have points inside and outside for the epsilon disk. So let's see here. So 3 minus I over 2 is an element of the boundary of U. It's a boundary point, right? Right? How about this? What if I look at down here, this point, maybe, I don't know, that's maybe 2 minus 2i, that point right there. What can you tell me about that? Is that an interior point? No. Is it a boundary point? But it's not in the set. But did I say that boundary points had to be in the set? No, we did not. So boundary points can be outside of the set. Yeah.
So since it says there exists an epsilon greater than 0, couldn't you really pick any point in U and you could pick an epsilon such that the disk has points inside and outside?
Yeah, I think that's... Yeah, that's not quite right, is it? How would you fix it?
I would change it to a universe.
Just for all epsilon?
Yeah.
Yeah. Yeah, I think that's right, Shane. Thank you. It was bothering me. I was like, something feels off about this. But so we'll just make that a for all, and I think we're good. But really, the idea is that for arbitrarily small epsilon, you have points inside and outside, right? But just for the sake of making a less clumsy definition, rather than saying for all epsilon sufficiently small, we have points. Anyway, what you said is better. So 2 minus 2i is a boundary point, yeah? 2 minus 2i is an element of the boundary of U, but 2 minus 2i is not an element of U. So what does this tell us about U?
It's an open set.
Hence, the boundary of U is not a subset of U, right? If there's one point in the boundary which is not in U, game over, it can't be a subset, right? Because subset means any point in the set is automatically a point in the superset. But U is not open either, because 3 minus 1/2 is a point in U which is not interior. So this set U is neither open nor closed. It is possible for a set to be open. It is possible for a set to be closed. It's possible for a set to be neither open and closed. And it's also possible for a set to be both open and closed. They can be both. So like, let me show you. So here's two stupid examples of sets which are both open and closed. So like example 2, which is really kind of more of a comment, which is the empty set is both open and closed. It's open because is every point in the empty set an interior point? Well, yeah, because there are no points in the empty set. So it's vacuously true. The empty set's open. Is it closed? Well, if you accept my theorem, what's the complement of the empty set? What's C minus the empty set? It's C again, right? And this is open. Because every point in C is interior, because every point is contained in a disk, right? You can always tick any point. It's inside the disk of radius 1. There you go, I'm done. Centered at that point, you know? So the empty set is both open and closed. And you know what else is both open and closed? The whole complex plane, by essentially the same logic, right? The whole complex plane is also both open and closed, right? Why? Because every point in C is an interior point. And what's the complement of the complex plane? It's the empty set, which we already know is open. So again, we'll use this theorem when it's convenient to us. Of course, another way you could look at it is what's a boundary point of the complex plane? What's the boundary of the complex plane?
There is none.
There is none, that's right. Yeah. There's no point which has an open disk around it, which has points both inside and outside C. So, yeah. Okay, so these are these are basic topology ideas. There's more. Let's see here. Let me work one. Let's see here. My example 3, I actually have proof that the intersection of two open sets is open. That might be worth actually looking at for a minute with you guys. So let's let U1 and U2 be open, right? Then if we look at the intersection, if U1 intersect U2 is empty, then the intersection is open, right? Because of example 2, because the empty set is an open set. So otherwise, there exists, let's say, Z0, an element of the intersection of U1 and U2, right? And so I can draw a picture, like schematically. So maybe this is U1, and this is U2. I should have color coded them. Oh well. So Z naught would be like perhaps here, right? Now, so Z naught is it's an open set. I mean, excuse me, it's an interior point, right, of U1. What does that mean? That means we can find like epsilon 1 such that the disk of radius epsilon 1 is a subset of U1, right? But it's also an interior point of U2, right? So that means we can find an open set around Z naught that's interior to U2. Now that one could, you know, maybe that one would look like this here, you know? All right, so it's like epsilon 2, epsilon 1. So the disk of radius epsilon 2 centered at Z naught would be a subset of U2, right? So let me explain what I'm trying to do in this example. You may not know what I'm doing because this is all new to you, right? I'm trying to give you a proof that the intersection of two open sets is open. So there's two possibilities. Either they don't meet, right? Which means it's empty, that's open by the previous example. Or they meet, there's some point that's common to them, right? And so we'd like to show that that point is an interior point to the intersection, right? So the intersection here, in my picture, the intersection looks like what? Like, it's like this business here, right? Everything inside this area here, right? I don't want to shade it all and it'll get too busy, but you get the idea, right? So how can I get an open disk inside the intersection? What do I do? I mean, for my current picture, I would use what? I just use epsilon 1, right? But this is just a picture. Epsilon 2 could have been the smaller one, right? But think about it. There's just something that's basically true about disks. If we have disk of R1 centered at Z naught, it is going to be a subset of disk of R2 centered at Z naught, provided what?
R1's less than R2.
Yeah, R1's less than or equal to R2. That's right. And it would be a strict inclusion if we had less than. That's true. So how can I pick an epsilon with the data that I have? What do I do? So notice the disk of radius epsilon of Z naught. I gotta say the epsilon first. Epsilon equal to the minimum of epsilon 1 and epsilon 2 gives the disk of radius epsilon centered at Z naught as a subset of the disk of radius epsilon 1 of Z naught, and it gives the disk of radius epsilon of Z naught as a subset of the disk of radius 2 at Z naught, right? When you draw a picture like this, you have to be careful not to let it like inform your argument too much. You have to think a little bit more abstractly, right? Have you guys had geometry with Sprano? Are you in there right now? So you'll learn to draw crooked pictures when you're trying to make lines straight, you know? Because you don't want to assume the line is straight. So you do things like make it crooked to prove it straight, something like that. I don't know. So I think you should do geometry with coordinates personally. I think not introducing coordinates for geometry is it's a sad situation. But such is the situation in modern geometry. Which is thoroughly not modern, by the way. But anyway, so that's kind of funny. Like you're using Euclidean geometry in there. It's like arguably the oldest part of math. We call it modern geometry. Anyway, so this disk of radius epsilon centered at z naught is a subset of this and that, which are respectively subsets of what? U2 and U1, right? Which means that, we find thus the disk of radius epsilon centered at z naught is a subset of the intersection, right? Therefore, z naught is an interior point. But z naught was an arbitrary point in the intersection. Therefore, the intersection is open. All right? Now, I think the proof I have in the notes is perhaps a little bit better, but there you go. All right, let me tell you some other things that are open. The open disk of radius epsilon is open. I'll prove it by pictures for you guys today. So if I have here's my disk centered at z naught, radius epsilon, where if you pick any point in there, is it clear that you can put another disk that's contained inside the disk? What do you guys think? I mean, I think it's just geometrically obvious, right? If I pick this point here, I could do like this disk, right? If I pick this point right here, I can do a wee itty bitty disk. But you can make the disks as small as you want, right? Yeah? And so you could choose the radius of the disk based on, like, well, anyway, I'm not going to go through the analytical proof here. I'm just going to give you proof by picture for today. All right? We could make this more rigorous by actually, picking a point, say, like, this could be Z1, right? To finish this, like, analytically, you need to, like, for Z1, an element of the disk of radius epsilon at Z naught, need to construct epsilon such that the disk of radius epsilon centered at Z1 is a subset of the disk of radius epsilon at Z naught, right? And what that means is you need to have the criteria that the modulus, so then to prove this, you pick a point in here and show that it's in here, right? So to actually carry that out, you'd have to define the epsilon, pick the point in the disk of radius epsilon at Z1, and actually show that that inclusion's made. Yeah? Which I have assigned as homework in here before. So I might have assigned. That's why I wanted to print out mission 2 to see if it was in there. I don't know if it's in there or not. It may be in there. So I'm going to be careful not to do it for you guys. Yeah. All right. So next up, there's an easier problem we can kind of like do. We can talk about like how to prove a half plane is open. For instance, we can talk about like the upper half plane. For the purpose of this example, we'll say Z such that the imaginary part of Z is, well, I guess we can make it greater than 1 just to make it slightly more interesting. So here's y equals to 1, right? And so down here you've got the real axis, right? And here's your imaginary axis for context. And so my claim is that if we, just dot the edge of this, then what's above that is an open set. Can we prove that? What do you guys think? I think we'll be able to do that here now without too much mental effort. Let's figure it out. So what I have to do is I have to pick an arbitrary point in the set I'm trying to prove is open, all right? So let's call that Z0. Okay, so let Z0 be an element of the set I'm calling H for half plane. Then let's say Z0 is equal to X0 plus I Y0. I mean Y0, right? Sorry. Oh. Bah. It smells like death. We've been through this before. Ugh. Yowzers. Sprano was telling me there's a particular green marker in the break room, or the conference room, that's particularly insidious. Now, to say this is an H, what do we have? We have X0 as a real number, so we don't really get much information about that at all, right? But we do have something very specific about Y0. Y0 is what? It's greater than 1, right? Yeah? So how far is this? What's this distance?
1 minus Y0.
1 minus Y0?
Or Y0 minus 1.
Y0 minus 1. All right, votes for 1 minus Y0, votes for Y0 minus 1. You're like, well, you wrote Y0 minus 1, so it better be that, right? No. But yeah, you're right. So that's positive, right? Because Y0 is greater than 1. All right. So what should we make the radius for our disk centered at Z0 that's contained within the set?
Y0 minus 1 over 2.
Yeah, you could do that. We could even be greedier, though. We could just let it be Y0 minus 1, right? Because it's an open disk. It doesn't actually, you know. But I will honor your request, Shane, and make it like that. All right. So let's let epsilon equal the 1/2 of Y0 minus 1, right? We wish to show that the disk of radius epsilon centered at Z0 is a subset of this allegedly open half plane. All right? How do we do that? How do you show something's a subset of something else? What you have to do is you have to pick a point in it, right? So I guess we haven't used Z yet, right? So let Z equal to X plus IY be an element of the disk of radius epsilon centered at Z0. Then what does that mean? Then the modulus of the length of Z has to be, the length of Z minus Z0, right? Has to be less than epsilon, right? By definition. Because the disk of radius epsilon centered at Z0 is a collection of all Z that are distanced at most epsilon, not even epsilon, away from Z0. Now let's unwrap that. What does that actually mean? So what we're saying is, well, you know, fun fact. Notice that the absolute value of y minus y0 is less than the absolute value of z minus z0, or equal to it, which is less than epsilon. This is one of the fundamental properties of the complex length, is that a complex quantity has the magnitude of it is larger than equal to either the real component or the imaginary component, right? So the imaginary component of z minus z0 is just nothing more than y minus y0, right? So we can write this. But then you see we chose epsilon to be 1/2 of y naught minus 1. All right. Now we have absolute value inequality, so we can unwrap that, right? What does it mean if we have the absolute value of y minus y naught is less than 1/2 of y naught minus 1? What does that tell me? In fact, that's equivalent to the compound inequality, minus 1/2 y naught minus 1 less than y minus y naught less than 1/2 y naught minus 1. This is like a fundamental fact about absolute value, right? Do you guys know this? If I have the absolute value of b is less than delta, that's true if and only if like minus delta is less than b is less than delta. If you have an absolute inequality, absolute value inequality, that is how to change it into a compound inequality. Now, if the absolute value of b is greater than delta, well, that's a different story altogether. I've tried to teach this to many a college algebra class. They refuse to learn. I don't put deltas in there. I'm not a monster. But there's numbers in that class. OK, so what does this tell us? Add y naught across this inequality. What do you get? We've got y naught over 2, right? Plus 1/2 less than y less than, I'm adding y naught. I get 3/2 y naught minus 1/2. What did we know about y naught? It's greater than 1, right? That was given, remember? This right here. So if I know that, what can I do down here? This is greater than what? 1/2 plus 1/2, right? Oh, you say 3/2? Did I do something wrong?
No, I didn't.
And that, of course, is what? That's 1. So y is greater than 1. Yeah? Is that good? What does it mean y is greater than 1? So we have z equals to x plus iy with y greater than 1. Thus, z is an element of the half plane. And so the disk of radius epsilon centered at z naught, the disk of radius epsilon centered at, z naught, I'll get it eventually here, guys, is a subset of H, as we claimed. Because we picked an arbitrary point in this disk, and we showed that it fell within the half plane. Is there something? No? OK. I might have made a mistake here. It feels too tight, yeah.
Did we have, so we didn't have, we don't have to plug in 1 for y naught on the right side, like we're.
Oh, yeah.
Y naught, I mean, it's still 1, but.
It is, there, yeah, I mean, that's the thing is we didn't even need to use this.
Okay.
Yeah. So we're just interested in showing that y is greater than 1. I have a suspicion there's some kind of arithmetic error in here somewhere because it feels too close. Like we shouldn't have had to do Shane's suggestion of 1/2. It should have worked without that, and I feel like it just barely worked with what I have, which makes me think there's an error in here. But it's not that interesting. We need to move on. So the general point of this is correct, but I'm suspicious of the specific inequality details here. Okay. Let us move on. So what's up next? We have, oh my goodness, I am spending too long on this. I should have made these homework problems, not class examples. Yowzers. All right. So I don't, this kind of argumentation I just did for proving that's open, it's not really something that sticks with us the rest of the course. Like, we don't find ourselves making arguments like that much after this point. Mostly the point of that is to really properly digest the definition of open set. Like, that's the point of that, is for you to try to more deeply understand what we mean by open and what's involved in proving something's open. You know, I think about two words. Analytically, the kind of thing we just did, I would say, is an analytical proof, right? On the other hand, two of the examples I gave a graphical proof, right? Like, my proof for example 4 wasn't like it was a geometric proof, right? I essentially just drew a picture and tried to argue that way. And I like to ask you guys both in here. Sometimes I just want to ask you to, like, you know, give me some kind of brief geometric reason that one of the things I'm asking is true. But then other times, yeah, we really do want to supply like a complete analytical argument. So I try to let you know which one's which, because obviously the geometric proof is like way, way easier and faster, right? So, you know, this is not the first time you've heard stuff like this, right? Like, how do you prove that the integral from, if you got like a partition of a set from A to B and then C is in the middle, how do you prove the integral from A to B is actually the integral from A to C plus the integral from C to B? I mean, you draw a picture, right? So like the area under the curve from A to C plus the area under the curve from C to B should be the area from A to B, right? That's a geometric proof. But what would it actually take to prove that directly from like the Riemann definition of the integral?
FDC part 1, right?
No. No. Directly from it's a property of integration, that the integral over a subset is the sum of the integrals over. If you have a set which you're integrating over, and you have two sets whose union is the whole set, then the integral over the whole set is equal to the sum of the integral over one subset plus the integral over the other subset. Like, it's nothing about fundamental theorem of calculus. It's just like a basic property of the integral, which we never prove in calculus. We just draw a picture and we say it's true because it's geometrically obvious. But to actually prove that, by taking a given Riemann sum from A to B and splitting it into two different Riemann sums, one from A to C, one from C to B, and parsing how that partition and limit actually sorts out into two things, is actually rather involved. I know this. It took me like a whole faculty meeting to work it out. Like 3 hours. I have to reach a level of boredom to do that kind of proof that only is supplied to me by faculty meetings. So, yeah. Anyway, okay, so this is important notation. I like this. This notation's really, really slick. It's cool. So for us, A to B is, check this out. It's A plus T times B minus A, such that T is an element from 0 to 1.
Is that the definition you were going to give over here?
This is a directed, maybe, directed line segment. That's a historical question. I don't know. Where was your theory?
You were about to write a definition, but
Yeah, I think that was it. It was that definition. In fact, I was about to write there, and then I got sucked into that half plane example, which is more likely one of your homework problems. Something like that is almost certainly in the homework. It's been on like most of my tests of recent years. But anyway, I am trying to woo the engineers, which might push that off the test. I don't know. So anyway, so this is a directed line segment. I just think that's a really neat notation, right? Because we before had this like an interval, right? So like before, if somebody told you 4 to 3, you should have been like, no, you can't do that, right? But here, that just means, well, you're on the real line. Here's 4, here's 3. This is just the line segment which goes from 4 to 3. Yeah? And if you wanted a line segment that went from, say, 1 plus I over here to 10 plus, 3i or 2i or whatever, like that, well, it would be 1 plus I, comma, 10 plus 2I. I love this notation. It's just so slick. It's very cool. So that's a directed line segment. Definition: subset of the complex plane is called star-shaped with star center Z naught, all right, if there exists Z naught in U such that each Z in U has the directed line segment from the star center to Z a subset of U. Star-shaped. So, like this. That's star-shaped. Like I could make, the star center doesn't have to be unique, but here's one. I could put it here, right? If this is the star center, then any point I pick, right? I can get to any point in this shape by a directed line segment which starts at Z naught. Another set which is star-shaped, which is perhaps a little bit less obvious, is the slit complex plane. So if I delete the negative axis here, right? So the origin's deleted. Everything else is in here. The slit complex plane, we call this C minus. That's a star-shaped region. You can pick any point on the positive real axis as your star center. See, if I pick a point here, I can pick a line shallow enough that it gets to there. And I can get everywhere else also. So the slit complex plane is also star-shaped. But the punctured plane is not. Like if I throw out the origin and just that, right? That wouldn't be star-shaped. Do you guys see why that is? Because if I just try to look at the punctured plane, right? Throw out the origin, wherever I put my star center, like here, right? It necessarily can only get to there, but it has to be missing all this, right? So like wherever you put the star center, opposite the origin, on the other side of it, you have to be missing that ray. There's no way you can get to it with a directed line segment. So the punctured plane, not star-centered. Not star-shaped, rather. All right? Another thing we should define is a polygonal path. A polygonal path is a union of finitely many line segments which are placed end to end. All right, so like a polygonal path might look like this. There we go. Each one of these is a directed line segment, right? And the union of all these directed line segments is a polygonal path. A union of a finite collection of directed line segments. All right? And each one starts where the last one ended, you know? I don't know why I made so many of these. I'm an idiot. All right. The next definition is connected. What does it mean for a set to be connected? Any ideas?
It seems like for each point in the set, you can form any loop of points in the set around that point.
You were thinking of something else, but let's see here. Definition. We'll get to that, but not maybe here. So S, a subset of C, is connected, all right, if and only if there exists a polygonal path contained in S between any 2 points in S. Now, I will say that I would say, properly speaking, the definition I just gave you is pathwise connected. This is really the definition of pathwise connected. It just so happens that in the context of the complex plane, that path connected is equivalent to connected. But in the broader study of topology, path connected and connected are different things. So you can prove there's a theorem, all right? And I won't prove this because it's not a topology class, but you can prove that another way to characterize S being connected, you could say S is connected if there does not exist a separation of S. And you might wonder, well, what is a separation of S? All right. Well, a separation of S is a pair of sets, all right, which are that is, all right, so that is, you know, there does not exist, let's say, U1 and U2 subset of S for which S is equal to the union of U1 and U2, and yet they don't meet. So like U1 intersect U2 is empty. And I think if you just like draw a picture of that, right? So like, you know, so S would maybe look something like this then, right? Here's my U1, here's my U2. They don't intersect, right? It's fairly clear that that is also not path connected, right? Do you see why? I mean, I hope you can see why. I'm supposing U1 is this set here, right? And U2 is that set here. I wish we had a chalkboard. More than any other day, whenever I want to shade things, like whiteboards just feel so. So if I take a point here, right, and I take a point here, then there's just, and I mean, okay, fine. We're dealing with polygonal paths, so I have to do this. Like, generally speaking, people look at continuous paths, not just these unions of directed line segments. Looking at unions of directed line segments is just kind of a simplification for the complex notes, yeah? And the same way star-shaped is really a kind of a juvenile version of simply connected. It's just an easier thing to make proofs for. But it's the grown-up version of that is simply connected. But we talk about star-shaped because it's just a little bit easier to find proofs for. But simply connected is like a more continuous version of that in some sense. And that's where we talk about the loops deforming and such. But this is just connected. Connected. All right, so here, give you an example. I don't know what example I'm on. Let's call it example 10. So suppose you had this space. Whee! All right? And so this is my space. Is this connected? It is, because if I take any point here and say down here, I can go to that point right there, and then I can go like that, you know? So I can pick any point P and go to any point Q by some path. It's path connected. If, on the other hand, I was to do something like this, right? So that this point right here was absent, you know, not there, not in the set, then that would not be a connected set, the union of those two things, because there's no way to get from the upper to the lower, all right? So a lot of times in here, we work a lot with the following definition. So here it is. An open connected set is called a domain. We say R is a region if R is equal to D union S, all right, where D is a domain and S is a subset of the boundary of D. So like that set that was neither open or closed earlier today, that one, that would be an example of a region. Because it, you know, it's not open, but it only contains, but it is the union of like the open rectangle. If you go back to that example, like the open rectangle is a domain, and the boundary of that open rectangle, we just did nothing more than union the vertical sides of the rectangle, if you go back to that example, right? So like examples, this would be a domain, something like this. Your foot is weirding me out. It felt like in my ear, it felt like it was here. I'm like, it felt like you got up out of your seat and you're like walking up to me. Like my ears are like playing tricks on me. That's bizarre. So this is not a domain. This is not a domain, right? Because it's not an open set, because it has parts of that boundary which are not, these parts on the edge are boundary points, which are not interior points. All right, anyway, so on the other hand, it is a region, right? Because if you fuzzify the edges, that is an open connected set, right? Because you can go around the hole, right? You can just walk around the hole. And the part that's not part of the domain is just part of the boundary of the domain, which we've unioned. So a region, a region doesn't have to be closed, but you know, a closed set would be a region if it was obtained in this way. Okay, so there are other closed sets which are not regions, like a curve. See this? This is a set. That is a closed set. A curve is a closed set. Because if you look at it, any point here, right? Any point on there is a boundary point, right? Because there's